My name is Skylar McCaw, and this is my Lab 1 video about charged tapes. The goal of this experiment was to charge a piece of tape and see how it interacted with other objects and measure the excess charge it has. The tape was charged by first laying down a base layer of tape and then placing a second layer on top of it. The second layer is then ripped off rapidly to charge it. Touch the tape as little as possible and place it on the edge of a table hanging off to conduct the rest of the experiment. Bring your hand close by, and if the tape is attracted to it, that means it's charged. Then, rub a pencil against hair, negatively charging it, and bring it close to the tape. You'll observe that the pen repels the tape, meaning that the tape has a positive charge. Make another charged tape the same way and bring the two together and see how they repel each other. Now, it's time to figure out the force each tape exerts on the other and therefore the charge they possess. All that is needed to do this is to set up the tapes as shown in the diagram above and measure their distance apart. For my experiment, the distance apart came out to be 0.0127 meters. Now, how do we get from this distance to charges? It's all based on a few physics concepts, including Newton's laws and Coulomb's law. But first, we have to clarify some basic assumptions we are making in order to use this method. First, we are treating the tapes as point charges, and second, we are assuming that the tapes have the same net charge. We are also saying that air resistance is negligible. When looking at a model for this situation, one that we will code later, the relationships between different forces is easy to see. Because the tape is not moving in the y direction, that means that the force of gravity is being offset by the force of the charged tape, so we were able to calculate the electric force that way, and it comes out to be 1.67 times 10 to the negative third newtons. Knowing the electric force, you can rearrange the equation and solve for the charge Q. And since the tapes have the same charges, the Q's are identical. For my tape, the Q's worked out to be 5.38 times 10 to the negative ninth coulombs. And now we calculate the number of deficient electrons, because it's positive, as well as the fraction of atoms that gave up electrons. The equations for these values are shown above, starting with there being 3.36 times 10 to the 10th deficient electrons. Next comes the total number of atoms as being 2.05 times 10 to the 17th atoms. And from there we get the ratio of deficient electrons to atoms to be 1.63 times 10 to the negative 7th electrons per atom. Here is the code I created to do the calculations and create a model. I started by defining constant values and then went right into the gravitational and electric forces. I then calculated the number of deficient electrons as well as the ratio of deficient electrons to total atoms. The model created with the code is shown off to the right. What if electrons had a positive charge and protons had a negative charge? The same basic relationship would still remain. Like charges would repel and opposite charges would attract. Since the tape was positively charged, it is deficient in electrons, but would now have an excess of electrons. Besides that, nothing would change. Why is it important to handle the tape as little as possible? Handling the tape causes electron transfer to occur between the hand and the tape, reducing its charge. And since we want the tape to have a charge, touching it as little as possible is key. That's all. Thanks for watching.